Hello hacker fellows, I just wired a pulse counter or frequency divider using only relays, old Russian relays, which are powered by low voltage and a charge switcher controlled by a push button. And when we chain these circuits, we can make a binary counter or frequency divider or whatever you want to call it. And the circuit is quite delicate. It's not difficult, but there are some little details that matter a lot. I have just wired a little example circuit where we have the power supply coming in plus 3 volts and it's drawing 32 milliamps with a little cap to filter everything because it's quite noisy. Power supply wires are doubled and short because there's some resistance here. And so we have the 0 volt. I measure everything with my multimeter, and we have a little relay RES15 from Russia, which is a low voltage. This one is a low voltage model. The coil is in series with the 39 ohm resistor, and in fact it's the same resistance as the coil. So we have the power supply coming in, going through the resistor and going through the coil, and the voltage at the coil is halved, so we have about 150 volt, which is half of the power supply. So far so good. And the output is wired to LED, and it's turned on when it is at rest. So when I turn the power off, the LED turns off, and on when I turn the power on. So it shows that there's no current going, which is interesting. But we have the 150 volt at the coil, and at this level the coil is partly energized and there's the hysteresis. And here I have the wire that goes to the middle point between the resistor and the coil, and I will alternate. So when I touch one wire, so for the 0 volt, if I short to 0 volt, the coil, it stays off, and when I connect to +5, the relay closes and the LED turns off. So we have hysteresis because the relay keeps the state, because the resistor powers the coil just halfway between the two stable states, and in between it needs some energy to go from one state to another. I connect to the 5 volts and the power supply drops because the wires are a bit resistive. And of course there's a short circuit, so the current draw doubles, which is why I put the capacitor to filter things. So I have a bistable system, which is pretty neat, but it requires a pretty clean power supply. So far so good. The relay is latching, and there's a little problem because when I touch the wire here, the contact is not great. So I wired a push button connected to a different power supply, and they are connected by the common ground. So the normally open contact can be wired to either polarity, and so there is a nice contact, but still when I keep the button pressed, the current increases as long as I keep the button pressed. So I want to reduce that current, and we have a little capacitor. Well, it's a big one because it's 470, and this will hold and store some energy that will be released to the coil when the circuit is switched from the input to the output. So there is only one short spike. There I connected the capacitor at the middle point of the SPDT switch. So one branch, the normally closed circuit, can be connected to one voltage, for example plus, and then the capacitor charges, and when we press the button, it discharges through the coil, and the relay will keep the state. So when we connect the capacitor to the other voltage, the relay keeps its new state, and there is only one short spike. So, and when we press again, there is no effect on the power supply because the charge is already there and it doesn't need more energy to charge it or to change it. And just like I did before with the SPDT switch, I can replace the wire and stop wiggling it and replace it with a proper SPDT switch. So this one switches between 0 and 5 and 3 volts and 5.5. So this will decide the voltage to charge the capacitor, and this one will switch the capacitor from the input to the output and change the state of the relay. So if I leave the data switch, it's a data like this, it gives 0 volt and there's no effect because it's already off. Yes, because there's the inversion. And then if I push and set the clock, plus 3 volts gets inside the capacitor and released in the coil, which opens the circuit for the LED. And so we have a sort of master-slave switch. We have a master-slave latch. I keep it held down. But the interesting thing is to have this SPDT switch replaced by another relay. Well, with all these experiments, one thing I have noticed is that power supply is important. The voltages are important because when I switch from when capacitor, when charges move, they create quite a lot of noise, and also the prototyping boards are not great. So there are a lot of naughty things happening. So that's why I use a different power supply there are two power supplies, one for the signal, one for keeping the coil energized. And this power supply can be quite noisy. It's not that important, but this one needs to be fairly well regulated. We have some margin, and there are some discrepancies or variations between coil characteristics. So this part is a sensitive part, and this one can be a noisy one. So the circuit has changed only a little bit. The capacitor is switched from the data to the coil by the relay, and the switch is just now a push button. So pushing it controls the relay, which transfers the data to the coil. This way, when I push, it turns off, release, turns on. The transfer occurs only during the transition between one to the other. So as long I can push the push button and still wiggle, and it won't change the output. So it's a true master-slave latch. Now let's get to the interesting part. Why did I do all this? Well, I just removed the data switch. It's not here anymore. And I've used the output from the relay and looped back to the clock SPDT relay. So one interesting trick is that I have powered the LED and the output from the secondary circuit. We will see why. So the output is negated, that's why the LED was on by default. So when the coil is de-energized, the LED turns on, so it shows the state of the relay. And this negation is brought to the capacitor, it charges the capacitor. And when I push this button, it transfers the charge to the coil, which latches, and since it's inverting, it turns the LED off. It's sometimes a bit picky. Yes, I had to boost the voltage a bit. So yes, we see we need quite a lot of energy to change the state. That's why the coil has to be powered by a different power supply. And this one doesn't vary much. But on the other hand, we have spike, which could disturb the hysteresis of the magnetic latch. So here what we have is a frequency divider or a pulse counter, because if we chain those circuits, they can count in binary the number of pulses. In this new version, I have replaced the bulky 470 microfarads capacitor with a smaller one with only 100 microfarad, and it still works, but I had to increase the voltage again because it has to be charged more at a higher voltage to have the same charge as the larger capacitor. So yes, I have to have separate power supplies, and it works nicely. Hope you enjoyed it.